Hi, my name is Sofia Conceição, and I'll present my teamwork lasigeBioTM at MedHop track. Can a link enhanced model compete with MedGemma? So the MedHop track is inserted in the BioCreative IX challenge, and it offers a curated dataset of 1,000 question-answer pairs that focus on diseases, genes, and chemicals from publicly available Wikipedia data with emphasis on rare diseases. This dataset serves as a benchmark for LLM-based systems in answering multi-step reasoning questions related to diseases. Despite their capabilities, LLMs are often associated with substantial computational resource requirements, so it is important to explore alternatives that minimize resource while being reliable. So our goal in this participation was to evaluate whether the implementation of retrieval augmented generation and chain of thought prompting with the lean Mixtral 7B instruct model could achieve satisfactory performance levels. In our work, we mainly used three models: the MedGemma 27B, Mixtral 7B Instruct version 0.3, and Gemma 3 1 billion IT from Google. MedGemma is trained exclusively on medical texts, specifically designed to enhance the understanding of complex medical texts and improve clinical reasoning. Gemma 3 1 billion 1B is a lightweight open source multimodal from Google with a large context window, but it is suitable for deployment in resource-constrained environments. Mixtral 7B Instruct is a fine-tuned model using a variety of publicly available conversation datasets. This last model, Mixtral, is the one that we select for the RAG systems due to our prior experience in other projects where it demonstrates a stable performance and minimal occurrence of hallucination. So we have two baseline models, Gemma and MedGemma, where we feed the queries to the system and the system outputs the answers. For our RAG models, we have Mixtral Wiki and Mixtral Onto, where we give the query to an intermediate system of Mixtral, where it performs name entity recognition to extract relevant biomedical entities. In the case of Biomedical Wiki, those entities are then we search for the Wikipedia pages and extract the Wikipedia introduction section and give that information joined with the query to our Mixtral system so it can output the final answer. The same is done for the Onto Mixtral, but in this case we give them ontology's definition using the Mondo ontology, which is an ontology that unifies disease resource and includes cross-reference from disease definitions from widely used ontologies such as human phenotype ontology, OMIM disease ontology, and so on. So the extract entities, we extract the definitions of those entities from the ontology and feed that information to Mixtral so it outputs the final answer. So for our results in the main official run, our best performing model is the MedGemma baseline, followed by the Mixtral RAG systems. Our results show that the provided external information was not sufficient to allow this small model, less specialized model, to perform well on the domain-specific tasks, where the baseline model achieved the better results. We also participate in the unofficial evaluation phase. We select our previous best model, which was the MedGemma baseline, and now we merge with our RAG systems, the Onto RAG system, and Wiki RAG system. Our best performance system was the MedGemma Onto, which underlines that the unstructured and noisy information that we get from the Wikipedia is not enough for the model to perform better, and it performs better with structure, more specialized information that is provided for the ontology. So as conclusion and future work, Mixrel benefits from the injection of external knowledge, but is not enough to match the performance of MedGemma baseline. Our best performing system was the MedGemma Onto, in which demonstrates the impact of integrated domain-trained language model, also with structured high-quality ontology information. The comparison between the two rack systems of MedGemma and Onto and MedGemma Wiki underscores the importance of high-quality and domain-specific external sources of information in boosting the system accuracy. Moreover, our reg models is restricted by the quality and coverage of the knowledge that we provide. In our case, we could only map 1,641 entities along with their definitions. So for most of the entities, there is lack of additional information. So for future work, we aim to improve the entity mapping by incorporating advanced name entity linking techniques, also fine-tuning the smaller language modules and integrating them with our querying approaches, and perhaps generating a structured knowledge graph from the biomedical free text found in Wikipedia, so it gives a more structured information to our systems. Thank you very much.